Hello there. Tonight, we descend beneath the surface of the visible world, past the realm of molecules and atoms, into a dimension where certainty dissolves and reality becomes a symphony of probabilities. Here, in the quantum realm, particles exist in multiple states simultaneously. Information travels instantaneously across cosmic distances, and the very act of observation reshapes the fabric of existence. This is not science fiction. This is the strange, beautiful truth that underlies everything you see, touch, and experience. Over the next 2 hours, we will explore 100 carefully curated facts about quantum physics, wave-particle duality, superposition, entanglement, and the mysterious principles that govern the subatomic universe. Each fact is a doorway into wonder, a gentle invitation to contemplate the invisible architecture of reality. You need not understand every nuance or equation. Simply allow these ideas to wash over you like waves on a shore, each one carrying you deeper into relaxation, deeper into the quantum dream. So settle into your pillow. Let your breathing slow and prepare to drift through the looking glass of the infinitesimally small, where the rules you know dissolve into something far stranger, far more beautiful, and infinitely more mysterious. At the turn of the 20th century, physicists believed they had nearly completed the grand project of understanding nature. Classical mechanics, electromagnetism, and thermodynamics seemed to explain the cosmos with elegant precision. Yet beneath this confidence, small anomalies festered, tiny experimental results that refused to conform to the established laws. One such puzzle involved blackbody radiation, the light emitted by heated objects. Classical theory predicted that as you examined shorter and shorter wavelengths, the energy should climb toward infinity, a catastrophic prediction known as the ultraviolet catastrophe. But nature did not behave this way. In 1900, a German physicist named Max Planck proposed a radical solution. Perhaps energy was not continuous, but came in discrete packets, which he called quanta. This single assumption, born from mathematical desperation rather than philosophical conviction, resolved the paradox completely. Planck himself was unsettled by the implications, viewing his quantum hypothesis as a temporary mathematical trick. He could not have known that this moment marked the birth of an entirely new physics, one that would unravel our intuitions about reality itself. The quantum, that indivisible unit of energy, became the first thread pulled from the fabric of classical certainty, and as physicists continued to pull, the entire tapestry began to transform into something unrecognizable, something shimmering and strange. For centuries, scientists debated the nature of light. Isaac Newton championed the corpuscular theory, imagining light as a stream of tiny particles. Later, experiments by Thomas Young and others demonstrated interference patterns, phenomena that could only be explained if light were a wave, rippling through space like sound through air. By the 19th century, the wave theory had triumphed, and light was understood as an electromagnetic oscillation. Then came Planck's quanta, and in 1905, Albert Einstein extended this idea to explain the photoelectric effect, the emission of electrons when light strikes certain metals. Einstein proposed that light itself was quantized, traveling in discrete packets of energy called photons. This was not merely a return to Newton's particles. It was something far stranger. Light, Einstein suggested, possessed a dual nature. Light, Einstein suggested, possessed a dual nature. In some experiments, it behaved as a wave, creating interference patterns and diffracting around obstacles. In others, it acted as a particle, delivering energy in localized, countable chunks. This wave-particle duality defied common sense. How could something be both spread out and localized, both continuous and discrete? Yet the experimental evidence was undeniable. Light refused to be confined to a single identity, existing instead in a superposition of possibilities, revealing one face or the other depending on how we chose to observe it. This duality would become a cornerstone of quantum mechanics, a reminder that nature, at its most fundamental level, does not conform to the either-or logic of our everyday experience. When we think of an electron orbiting an atomic nucleus, we might imagine a miniature solar system, with the electron tracing a smooth, continuous path around the central proton. But quantum mechanics paints a very different picture. Niels Bohr, building on earlier work, proposed that electrons occupy specific energy levels, or shells, around the nucleus. An electron cannot exist between these levels. It must reside in one or another, like a person standing on the rungs of a ladder, rather than floating in the space between. When an electron absorbs energy, it jumps instantaneously from a lower level to a higher one. When it releases energy, it drops back down, emitting a photon whose energy corresponds exactly to the difference between the two levels. This transition is called a quantum leap, and it is truly instantaneous. There is no intermediate state, no gradual motion from one level to the next. The electron simply ceases to exist in one location and appears in another, as if teleporting through the intervening space. This discontinuous behavior was profoundly unsettling to physicists, raised on the smooth, deterministic equations of classical mechanics. Yet it explained the discrete spectral lines emitted by atoms, those sharp, specific colors that serve as atomic fingerprints. The quantum leap revealed that the subatomic world is fundamentally granular, a realm where change occurs not in smooth flows, but in sudden discrete jumps, like frames in a film rather than a continuous stream. In 1927, Werner Heisenberg articulated one of the most profound and counterintuitive principles in all of physics, the uncertainty principle. It states that certain pairs of physical properties, such as position and momentum, cannot both be known with arbitrary precision. The more accurately you measure an electron's position, the less accurately you can know its momentum, and vice versa. This is not a limitation of our measuring instruments or techniques. It is a fundamental feature of nature itself. At the quantum level, particles do not possess definite positions and momenta simultaneously. Instead, they exist in a state of intrinsic fuzziness, a cloud of probabilities that only collapses into a specific value when measured. Heisenberg's principle shattered the deterministic worldview of classical physics, where knowing the present state of a system allowed you to predict its future with certainty. In the quantum realm, such certainty is impossible. The universe, at its smallest scales, is irreducibly probabilistic. This uncertainty is not born of ignorance, but woven into the very fabric of reality. It means that there is a fundamental limit to knowledge, a boundary beyond which the universe refuses to be pinned down. And yet, this uncertainty is not chaos. It is governed by precise mathematical laws, a structured randomness that gives rise to the stable, predictable world we experience at larger scales. Heisenberg's principle is a reminder that reality is far stranger than our intuitions suggest, and that the quest for absolute knowledge must reckon with the limits imposed by nature itself. Few experiments in physics are as simple in design and as profound in implication as the double-slit experiment. Imagine a barrier with two narrow slits, and behind it, a screen that records where particles land. When you fire a stream of particles, say electrons, at the barrier, you might expect each electron to pass through one slit or the other, creating two distinct bands on the screen. But that is not what happens. Instead, an interference pattern emerges, a series of alternating bright and dark bands, as if the electrons were waves overlapping and cancelling each other out. This is strange enough, but the true mystery deepens when you send the electrons one at a time. Even when only a single electron is in flight, with no other particles to interfere with, the interference pattern still builds up over time. Each electron seems to pass through both slits simultaneously, interfering with itself, exploring multiple paths through space before arriving at the screen. But if you place a detector at the slits to determine which one the electron passes through, the interference pattern vanishes. The electron, now observed, behaves like a particle, passing through one slit and creating two simple bands. The act of measurement collapses the wave of possibilities into a single reality. This experiment reveals the heart of quantum weirdness. Particles exist in a superposition of states until observed, and the observer plays an active role in shaping reality. It is as if the universe remains undecided, holding multiple possibilities in suspension until a conscious measurement forces it to choose. Erwin Schrödinger, one of the architects of quantum mechanics, was deeply troubled by the implications of superposition. The idea that a quantum system can exist in multiple states simultaneously until measured. To illustrate the absurdity he perceived, he devised a thought experiment involving a cat, a sealed box, a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, breaking the vial and killing the cat. If the atom does not decay, the cat lives. According to quantum mechanics, until the box is opened and an observation is made, the atom exists in a superposition of decayed and not decayed states. Therefore, the cat must also be in a superposition, simultaneously alive and dead. Schrödinger intended this as a reductio ad absurdum, a demonstration that quantum mechanics, when applied to macroscopic objects, led to ridiculous conclusions. Yet rather than discrediting the theory, the thought experiment became one of its most famous illustrations. It forced physicists to confront the measurement problem. At what point does a superposition collapse into a definite state? Is it when a conscious observer looks, or when any interaction occurs? Does the cat itself count as an observer? These questions remain unresolved, spawning interpretations ranging from the Copenhagen interpretation, which privileges observation, to the many worlds interpretation, which suggests that all possibilities occur, each in a separate branching universe. Schrödinger's cat, poised between life and death, has become an icon of quantum strangeness, a reminder that the boundary between the quantum and classical worlds is far from clear. Albert Einstein famously called it spooky action at a distance, and it remains one of the most bewildering phenomena in quantum mechanics. When two particles become entangled, their quantum states become correlated in such a way that measuring one particle instantaneously affects the state of the other, no matter how far apart they are. Imagine two electrons created together in a specific quantum state. If one is measured to have spin up, the other will immediately be found to have spin down, even if they are separated by light years. This correlation is not due to any hidden communication between the particles. It is a fundamental feature of their shared quantum state. Einstein, along with Boris Podolsky and Nathan Rosen, argued in their famous EPR paper that this implied quantum mechanics was incomplete, that there must be hidden variables determining the outcomes in advance. But experiments, particularly those by John Bell and later Alain Aspect, have confirmed that entanglement is real and that no local hidden variables can explain it. The universe, it seems, is non-local at the quantum level. Information about the state of one particle is somehow encoded in the state of its partner, and measurement collapses both states simultaneously, regardless of distance. This does not allow faster-than-light communication, as the results of measurements are random and only reveal their correlation when compared. Yet entanglement suggests that the universe is far more interconnected than classical physics ever imagined. A web of invisible correlations linking particles across the cosmos in ways that defy our intuitions about space and separation. We often think of a vacuum as empty space, a void devoid of matter and energy. But quantum mechanics reveals that the vacuum is anything but empty. According to quantum field theory, even in the absence of particles, fields permeate all of space, and these fields are subject to quantum fluctuations. For brief moments, particle-antiparticle pairs spontaneously pop into existence, borrow energy from the vacuum, and then annihilate each other, returning the energy before the universe notices the debt. These are called virtual particles, and while they exist for only the tiniest fractions of a second, they have measurable effects. One such effect is the Casimir effect, where two uncharged metal plates, placed very close together in a vacuum, experience an attractive force. This occurs because the vacuum fluctuations between the plates are restricted compared to those outside, creating a pressure difference. Another consequence is the Lamb shift, a tiny difference in the energy levels of hydrogen atoms that can only be explained by the influence of virtual photons. The quantum vacuum is a seething, roiling sea of energy, a background hum of creation and annihilation that underlies all of reality. It suggests that nothingness is an illusion, that even the emptiest regions of space are alive with quantum activity. This vacuum energy may even be related to dark energy, the mysterious force driving the accelerated expansion of the universe. The quantum vacuum reminds us that the universe is never truly still, never truly empty, but always vibrating with the potential for existence. In the classical world, if you roll a ball toward a hill, it will only make it over the top if it has enough energy. If it lacks the necessary energy, it will roll back down. But in the quantum world, particles can sometimes pass through barriers, even when they do not have enough energy to surmount them. This phenomenon is called quantum tunneling, and it arises from the wave-like nature of particles. A particle's quantum state is described by a wave function, which extends through space, including into regions that are classically forbidden. There is a small but non-zero probability that the particle will be found on the other side of a barrier, having tunneled through rather than climbed over. This is not a metaphor. Particles genuinely appear on the far side of barriers without ever occupying the space in between, at least not in any classical sense. Quantum tunneling is not just a theoretical curiosity. It is essential to many physical processes. It allows protons to overcome the electrostatic repulsion in the cores of stars, enabling nuclear fusion and the production of sunlight. It is the mechanism behind alpha decay in radioactive nuclear potential well. It is also exploited in modern technology, such as the scanning tunneling microscope, which uses tunneling electrons to image surfaces at the atomic scale, and in tunnel diodes used in electronics. Quantum tunneling reveals that the barriers we perceive as absolute are, at the quantum level, permeable. and that particles navigate a probabilistic landscape where the impossible becomes merely improbable. In 1925, Wolfgang Pauli articulated a principle that would prove fundamental to the structure of matter. No two fermions, particles with half-integer spin, such as electrons, protons, and neutrons, can occupy the same quantum state simultaneously. This exclusion principle is the reason why matter has structure and solidity. If electrons could all occupy the lowest energy state in an atom, they would all collapse into the nucleus. And atoms as we know them could not exist. Instead, electrons fill up energy levels one by one, like guests filling seats in a theater, each occupying a unique state defined by quantum numbers. This gives rise to the periodic table, as the chemical properties of elements are determined by the arrangement of electrons in their outermost shells. The exclusion principle also explains the stability of white dwarfs and neutron stars. When a star exhausts its nuclear fuel and collapses, the electrons, or neutrons, are squeezed into ever smaller volumes. But the exclusion principle resists this compression, creating a degeneracy pressure that can halt the collapse, at least up to a certain mass. Beyond that limit, not even degeneracy pressure can prevent the formation of a black hole. The Pauli exclusion principle is a quantum rule with macroscopic consequences, shaping the architecture of atoms, the chemistry of life, and the fate of stars. It is a reminder that the laws governing the invisibly small ripple outward, structuring the entire universe. In quantum mechanics, the state of a particle is described by a mathematical entity called a wave function, usually denoted by the Greek letter psi. The wave function encodes all the information about the particle's position, momentum, energy, and other properties. But it does so in a probabilistic way. The wave function itself is not directly observable. Rather, its square gives the probability density of finding the particle at a particular location. This means that a particle does not have a definite position until it is measured. Instead, it exists as a spread-out cloud of probabilities, more likely to be found in some regions and less likely in others. For an electron in an atom, the wave function describes an orbital, a three-dimensional region where the electron is likely to be found. These orbitals have characteristic shapes, spherical, dumbbell-shaped, and more complex forms that determine the atom's chemical behavior. The concept of a probability cloud is deeply counterintuitive. It suggests that before measurement, a particle is not located at any specific point, but is smeared out across space, existing in a superposition of all possible positions. Only when an observation is made does the wave function collapse and the particle assumes a definite location. This collapse is instantaneous and remains one of the most mysterious aspects of quantum mechanics. The wave function is the heart of quantum theory, a mathematical description of reality that replaces the certainty of classical trajectories with the shimmering uncertainty of probabilities, a ghostly guide to the behavior of the subatomic world. One of the most philosophically provocative aspects of quantum mechanics is the role of the observer. In classical physics, observation is passive. You can measure a system without affecting it, at least in principle. But in quantum mechanics, the act of measurement fundamentally alters the system being observed. This is known as the observer effect, and it is intimately connected to the collapse of the wave function. Before measurement, a particle exists in a superposition of states, a blend of possibilities. The moment you measure it, the superposition collapses, and the particle assumes a definite state. But what counts as an observation? Does it require a conscious observer? Or is any interaction sufficient? This question has sparked decades of debate. The Copenhagen interpretation, championed by Niels Bohr, suggests that measurement is a special process that collapses the wave function, though it does not specify what constitutes a measurement. Other interpretations, such as the many worlds interpretation, avoid collapse altogether, proposing that all possible outcomes occur in branching parallel universes. Still others, like the decoherence approach, argue that interaction with the environment causes the appearance of collapse without invoking a special role for consciousness. The observer effect challenges our intuition that reality exists independently of observation. It suggests that the universe is participatory, that the act of looking shapes what is seen, and that the boundary between subject and object, observer and observed, is far more fluid than we ever imagined. In the quantum realm, we are not passive spectators, but active participants in the unfolding of reality. Every electron in an atom is uniquely identified by a set of 4 quantum numbers, which together describe its state within the atom. The principal quantum number specifies the energy level, or shell, determining how far the electron is, on average, from the nucleus. The azimuth-fold quantum number defines the shape of the orbital, whether it is spherical, dumbbell-shaped, or more complex. The magnetic quantum number describes the orientation of the orbital in space, and the spin quantum number indicates the intrinsic angular momentum of the electron, which can be either up or down. These 4 numbers, constrained by the Pauli exclusion principle, ensure that no 2 electrons in an atom share the exact same quantum state. This system of quantum numbers is not arbitrary. It emerges naturally from the solutions to the Schrödinger equation for the hydrogen atom and extends to more complex atoms through approximations. The quantum numbers determine the electron configuration of an atom, which in turn dictates its chemical properties, its place in the periodic table, and its behavior in reactions. They are the invisible labels that organize the subatomic world, bringing order to what might otherwise be chaos. The concept of quantum numbers reveals the deep mathematical structure underlying matter, a hidden architecture of integers and half-integers that governs the arrangement of electrons, the formation of bonds, and the diversity of the material world. In the quantum realm, identity is not a matter of substance, but of numbers, a precise specification of state within the probabilistic landscape of the wave function. Quantum mechanics began as a theory of particles, but as physicists probed deeper, they realized that particles themselves were not fundamental. Beneath the electron, the photon, and all the other denizens of the subatomic world lay something more basic. Fields. Quantum field theory, which emerged in the mid-20th century, reimagines the universe as a collection of fields permeating all of space. Each type of particle corresponds to a quantum field. There is an electron field, a photon field, a quark field, and so on. What we perceive as particles are actually localized excitations in these fields, ripples or vibrations that propagate through the underlying medium. Imagine the surface of a pond. The water itself is the field, and the ripples are the particles. When a photon is emitted, it is not a little ball of light being created from nothing. Rather, it is the electromagnetic field being excited into a higher energy state, manifesting as a quantum of energy. This perspective unifies particles and forces, treating them as different aspects of the same fundamental reality. Quantum field theory also provides the framework for understanding particle interactions. When 2 electrons repel each other, they do so by exchanging virtual photons, temporary excitations of the electromagnetic field that mediate the force. This theory has been extraordinarily successful, predicting phenomena with astonishing precision. The anomalous magnetic moment of the electron, for instance, has been calculated and measured to agree to more than 10 decimal places, making it one of the most accurate predictions in all of science. Quantum field theory reveals that the universe is not a collection of discrete objects moving through empty space, but a vast interconnected web of fields, vibrating and interacting in a cosmic symphony. In classical physics, spin refers to the rotation of an object around its axis, like the Earth spinning on its axis as it orbits the Sun. But in quantum mechanics, spin is something altogether different. It is an intrinsic form of angular momentum possessed by particles, a property they carry even when they are not moving or rotating in any classical sense. Electrons, protons, and neutrons all have spin 1/2, meaning their spin angular momentum is half of Planck's constant divided by 2 photons have spin 1. This quantum spin has no classical analog. You cannot visualize an electron as a tiny spinning sphere, because the math does not work out. Such a sphere would need to rotate faster than the speed of light at its surface. Instead, spin is a purely quantum property, a label that describes how a particle transforms under rotations. It has profound consequences. Spin determines whether a particle is a fermion or a boson, which in turn dictates whether it obeys the Pauli exclusion principle. Fermions, with half-integer spin, cannot occupy the same quantum state, giving rise to the structure of atoms and the solidity of matter. Bosons with integer spin can pile into the same state, leading to phenomena like lasers and Bose-Einstein condensates. Spin also gives rise to magnetism. The magnetic properties of materials arise from the alignment of electron spins, and techniques like magnetic resonance imaging exploit the spin of atomic nuclei. Quantum spin is a reminder that the properties we observe in the macroscopic world often have no direct counterpart at the quantum level, and that nature's fundamental attributes are stranger and more abstract than our everyday experience suggests. When light shines on certain metals, electrons are ejected from the surface, a phenomenon known as the photoelectric effect. In the early 20th century, this effect posed a puzzle for classical physics. According to the wave theory of light, the energy delivered to the metal should depend on the intensity of the light. Brighter light should eject electrons with more energy. But experiments showed something different. The energy of the ejected electrons depended not on the brightness, but on the frequency of the light. Dim blue light could eject electrons, while bright red light could not, no matter how intense. Moreover, there was a threshold frequency below which no electrons were emitted, regardless of intensity. Albert Einstein explained this in 1905 by proposing that light is quantized, arriving in discrete packets of energy called photons. Each photon carries energy proportional to its frequency, and when a photon strikes an electron, it transfers all its energy in a single interaction. If the photon's energy exceeds the work function, the minimum energy needed to free an electron from the metal, the electron is ejected, carrying away the excess energy as kinetic energy. Increasing the intensity of the light simply means more photons, which ejects more electrons, but does not change the energy of each individual electron. This explanation was revolutionary, providing strong evidence for the particle nature of light and earning Einstein the Nobel Prize. The photoelectric effect is now the basis for many technologies, from solar panels that convert sunlight into electricity to the sensors in digital cameras. It is a beautiful example of how a quantum insight can resolve a classical paradox and open the door to practical applications. In 1924, a young French physicist named Louis de Broglie made a bold proposal. If light, traditionally understood as a wave, could behave like a particle, then perhaps particles, traditionally understood as discrete objects, could behave like waves. He suggested that every particle has an associated wavelength, inversely proportional to its momentum. For macroscopic objects, this wavelength is vanishingly small, far too tiny to observe. But for particles like electrons, with very small mass and momentum, the wavelength can be significant. De Broglie's hypothesis was initially met with skepticism, but it was soon confirmed experimentally. In 1927, Clinton Davison and Lester Germer observed electron diffraction, a phenomenon where electrons passing through a crystal created an interference pattern, just like light waves passing through a grating. This was direct evidence that electrons, solid particles of matter, could exhibit wave-like behavior. The concept of matter waves is central to quantum mechanics. It explains why electrons in atoms occupy discrete energy levels. Only certain wavelengths fit around the nucleus in a stable, standing wave pattern, much like the harmonics of a vibrating string. De Broglie's insight also paved the way for the development of the Schrödinger equation, which describes how the wave function of a particle evolves over time. Matter waves are not just a theoretical curiosity. They are exploited in technologies like electron microscopes, which use the short wavelength of electrons to image structures far smaller than visible light can resolve. De Broglie's proposal was a crucial step in the unification of wave and particle concepts, revealing that, at the quantum level, the distinction between matter and radiation, between substance and oscillation, dissolves into a deeper unity. As quantum mechanics developed, physicists faced a conceptual challenge. The new theory made predictions that were radically different from classical physics, yet classical physics had been extraordinarily successful in describing the macroscopic world. How could both be correct? Niels Bohr addressed this with the correspondence principle, which states that in the limit of large quantum numbers, large energies, large sizes, large numbers of particles, the predictions of quantum mechanics must converge with those of classical physics. In other words, quantum mechanics does not replace classical mechanics, it generalizes it. Classical physics emerges as an approximation, valid when quantum effects are negligible. For example, the energy levels of an electron in a hydrogen atom are quantized, but as you move to higher and higher energy levels, the spacing between levels becomes smaller and smaller, and the electron's behavior begins to resemble a classical orbit. Similarly, the wave-like behavior of a particle becomes insignificant when the particle is massive or moving at high speed, and it behaves like a classical point object. The correspondence principle provided reassurance that quantum mechanics was not a wholesale rejection of previous knowledge, but an extension into new domains. It also served as a guide in the development of the theory, helping physicists check that their quantum equations reduced to the familiar classical equations in the appropriate limits. The principle reflects a deep truth about the structure of physical theories. New theories do not erase old ones, but encompass them, revealing the older theory as a special case. Classical mechanics is not wrong. It is simply incomplete, a shadow cast by the richer, stranger reality of the quantum world. One of the great mysteries of quantum mechanics is why we do not observe superpositions in everyday life. If an electron can be in a superposition of multiple states, why can't a cat, or a car, or a planet? The answer lies in a process called decoherence. When a quantum system interacts with its environment, absorbing photons, Colliding with air molecules, exchanging heat, it becomes entangled with a vast number of environmental degrees of freedom. This entanglement causes the coherent superposition of the system to rapidly decay, leaving behind a statistical mixture that behaves classically. The system appears to collapse into a definite state, not because of a mysterious measurement process, but because the environment continuously monitors it, washing out the quantum interference effects. Decoherence happens extraordinarily quickly for macroscopic objects. A dust particle in air decoheres in a fraction of a second. A human body decoheres almost instantaneously. This is why we never see macroscopic superpositions. The environment destroys them before they can be observed. Decoherence does not solve the measurement problem entirely, as it does not explain why a particular outcome is selected, but it does explain why the quantum world appears classical at large scales. It also has practical implications for quantum computing. Quantum computers rely on maintaining coherent superpositions of qubits to perform calculations. Decoherence is the enemy, causing errors and limiting computation time. Researchers are developing techniques to isolate qubits from their environment and to correct errors induced by decoherence. Understanding decoherence is crucial for bridging the gap between the quantum and classical realms, revealing how the strange probabilistic quantum world gives rise to the stable, deterministic reality we experience. In 1896, Dutch physicist Peter Zeeman discovered that when atoms are placed in a magnetic field, the spectral lines they emit split into multiple components. This phenomenon, now known as the Zeeman effect, provided crucial evidence for the quantum nature of atoms. According to classical physics, a magnetic field should not affect the frequency of light emitted by an atom. But quantum mechanics explains the effect beautifully. The energy levels of an atom depend on the quantum numbers of its electrons, including the magnetic quantum number, which describes the orientation of the electron's orbital angular momentum. In the absence of a magnetic field, different orientations have the same energy, a situation called degeneracy. But when a magnetic field is applied, the degeneracy is lifted. Each orientation acquires a slightly different energy, depending on how it aligns with the field. This causes the single spectral line to split into several lines, each corresponding to a transition between levels with different magnetic quantum numbers. The Zeeman effect was one of the first experimental confirmations of the quantization of angular momentum and the existence of discrete energy levels. It also revealed the role of electron spin, as the splitting pattern could only be fully explained by including the spin magnetic moment. The effect has practical applications as well. It is used in astrophysics to measure magnetic fields in stars and galaxies by analyzing the splitting of spectral lines in their light. It also plays a role in technologies like magnetic resonance imaging, where the interaction between nuclear spins and magnetic fields is exploited to create detailed images of the human body. The Zeeman effect is a window into the quantum structure of atoms, a visible manifestation of the invisible rules that govern the subatomic world. At the heart of every atomic neutrons are protons and neutrons, and at the heart of every proton and neutron are quarks, held together by the strong nuclear force. Quantum chromodynamics, or QCD, is the quantum field theory that describes this force. Just as electromagnetism is mediated by photons, the strong force is mediated by particles called gluons. But there is a crucial difference. While photons are electrically neutral and do not interact with each other, gluons carry a type of charge called color charge, and they do interact with each other. This self-interaction makes QCD extraordinarily complex and gives rise to a phenomenon called confinement. quarks are never found in isolation. They are always bound together in groups, forming protons, neutrons, and other particles called hadrons. If you try to pull two quarks apart, the energy you invest does not separate them, but instead creates new quark-antiquark pairs from the vacuum, which combine with the original quarks to form new hadrons. The strong force does not weaken with distance, as electromagnetism does. Instead, it remains constant or even grows stronger, like a rubber band that resists being stretched. At very short distances, however, quarks behave almost as if they are free, a property called asymptotic freedom. This was a surprising discovery, earning the Nobel Prize for David Gross, Frank Wilczek, and David Palliser. Quantum chromodynamics is essential for understanding the structure of matter at the deepest level, explaining why protons and neutrons have the masses they do, and why the universe is filled with stable atomic nuclei rather than a chaotic soup of quarks. It is a theory of immense mathematical beauty and complexity, a testament to the richness of the quantum world. In the late 1940s, Willis Lamb and Robert Rutherford conducted a precise experiment measuring the energy levels of the hydrogen atom. According to the Dirac equation, which combined quantum mechanics with special relativity, certain energy levels should be exactly degenerate, having the same energy. But Lamb and Rutherford found a tiny difference, a shift of about 1 part in a million. This discrepancy, now known as the Lamb shift, could not be explained by the existing theory. It was a hint that something was missing. The resolution came from quantum electrodynamics, or QED, the quantum field theory of electromagnetism. QED takes into account the interactions between the electron and the virtual photons that constantly pop in and out of existence in the quantum vacuum. These virtual photons create a cloud around the electron, slightly altering its effective charge and energy. The Lamb shift arises because electrons in different orbitals interact differently with this vacuum fluctuation. The calculation of the Lamb shift was one of the first major successes of QED, and it demonstrated the reality of virtual particles and vacuum fluctuations. The agreement between theory and experiment was stunning, confirming that the quantum vacuum is not empty but teeming with activity. The Lamb shift is a tiny effect, but it has profound implications. It shows that even the simplest atom, hydrogen, cannot be fully understood without accounting for the quantum nature of the electromagnetic field. It also paved the way for precision tests of QED, which have since become some of the most accurate predictions in all of physics. The Lamb shift is a reminder that the universe is far more intricate than it appears, and that even the smallest deviations from expectation can reveal deep truths. In 1924, Satyendranath Bose sent Albert Einstein a paper describing a new way to derive Planck's radiation law, treating photons as indistinguishable particles, obeying a particular kind of statistics. Einstein extended Bose's ideas to atoms, predicting that at extremely low temperatures, a gas of bosons, particles with integer spin, would undergo a phase transition. All the atoms would collapse into the same quantum state, forming a single macroscopic quantum object. This state of matter, now called a Bose-Einstein condensate, remained a theoretical curiosity for decades because the temperatures required were so low, just a fraction of a degree above absolute zero. In 1995, Eric Cornell, Carl Wieman, and Wolfgang Ketter succeeded in creating the first Bose-Einstein condensates using laser cooling and magnetic trapping techniques. The achievement earned them the Nobel Prize and opened a new field of research. In a Bose-Einstein condensate, the individual atoms lose their separate identities, and the entire cloud behaves as a single quantum entity. The wave functions of the atoms overlap and synchronize, creating a matter wave that can be observed directly. This allows physicists to study quantum phenomena on a macroscopic scale, making the invisible visible. Bose-Einstein condensates exhibit bizarre properties, such as superfluidity, where the fluid flows without viscosity, and the ability to slow light to a crawl or even stop it entirely. They are also being explored for applications in precision measurement, quantum computing, and simulations of other quantum systems. The creation of Bose-Einstein condensates is a triumph of experimental physics, a demonstration that the strange predictions of quantum mechanics can be realized in the laboratory, and a bridge between the microscopic classical world. In 1922, Otto Stern and Walther Gerlach conducted an experiment that would become one of the foundational demonstrations of quantum mechanics. They sent a beam of silver atoms through an inhomogeneous magnetic field and observed where the atoms landed on a detector screen. Classical physics predicted that the atoms, with their magnetic moments oriented randomly, should produce a continuous smear on the screen. But that is not what happened. Instead, the beam split into two distinct spots, corresponding to two discrete orientations of the atomic magnetic moment. This was direct evidence of quantization. The magnetic moment could only take on certain discrete values, not a continuous range. The experiment revealed the quantized nature of angular momentum and provided early evidence for the concept of spin. The silver atoms used in the experiment have a single unpaired electron, and it is the spin of this electron that causes the splitting. The electron's spin can be either up or down relative to the direction of the magnetic field, and these two states correspond to the two spots on the screen. The Stern-Gerlach experiment is remarkable because it demonstrates quantum behavior in a simple visual way. It shows that measurement in quantum mechanics is not a passive observation, but an active process that forces the system into one of a discrete set of outcomes. The experiment also illustrates the concept of incompatible observables. If you measure the spin along one axis, you destroy information about the spin along other axes. The Stern-Gerlach experiment remains a cornerstone of quantum mechanics education, a vivid illustration of the discrete, probabilistic nature of the quantum world. Quantum electrodynamics, or QED, is the quantum field theory that describes how light and matter interact. It was developed in the 1940s by Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and others, and it represents one of the crowning achievements of 20th century physics. QED treats the electromagnetic field as a quantum entity, with photons as the quanta of the field, and describes how charged particles like electrons emit, absorb, and exchange photons. The theory is built on the principle of superposition. Every possible way an interaction can occur contributes to the final result, and these contributions are summed according to precise mathematical rules. Feynman introduced a powerful visual tool called Feynman diagrams, which represent particle interactions as simple pictures. Each diagram corresponds to a mathematical expression, and complex processes are broken down into a series of simpler steps. QED makes predictions of extraordinary precision. The anomalous magnetic moment of the electron, for instance, has been calculated to more than 10 decimal places and agrees with experimental measurements to an astonishing degree. This makes QED one of the most accurately tested theories in all of science. The success of QED also provided a template for other quantum field theories, including quantum chromodynamics and the electroweak theory, which together form the standard model of particle physics. QED reveals that the interaction between light and matter is not a simple deterministic process, but a rich tapestry of quantum fluctuations, virtual particles, and probabilistic outcomes. It shows that even the most familiar phenomena, like the reflection of light or the emission of radiation, are governed by the deep, strange laws of the quantum realm. In quantum mechanics, the act of measurement can have profound effects on a system's evolution. One of the most counterintuitive consequences is the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed paradoxes about motion. The effect states that if you measure a quantum system repeatedly and frequently, you can effectively freeze its evolution, preventing it from changing state. Imagine a radioactive atom that has a certain probability of decaying over time. If you measure whether it has decayed at very short intervals, each measurement collapses the wave function, resetting the system to its initial state if it has not yet decayed. The frequent measurements prevent the system from evolving into the decayed state. Even though left alone, it would decay. This is not just a theoretical curiosity. The quantum Zeno effect has been observed in experiments with trapped ions and other quantum systems. It demonstrates the active role of measurement in quantum mechanics, showing that observation is not a passive act, but an intervention that shapes the evolution of the system. The effect also has practical implications. It can be used to protect quantum states from unwanted transitions, a technique that may be useful in quantum computing and quantum information processing. The quantum Zeno effect is a vivid reminder that in the quantum world, watching a pot can indeed keep it from boiling, and that the boundary between observer and observed is far more permeable than classical intuition suggests. It reveals that time, evolution, and change are not absolute, but are influenced by the act of observation itself. In 1928, Paul Dirac sought to combine quantum mechanics with Einstein's special theory of relativity. The result was the Dirac equation, a beautiful mathematical expression that described the behavior of electrons at high speeds. But the equation had a strange feature. It predicted the existence of states with negative energy. At first, this seemed nonsensical. Dirac proposed that the vacuum is actually filled with a sea of negative energy electrons, and that what we perceive as empty space is this sea in its lowest energy state. A positive energy electron could fall into a negative energy state, releasing energy that this would violate the stability of matter. Dirac suggested that all the negative energy states are already filled, preventing such transitions. If a negative energy electron is given enough energy, it can be promoted to a positive energy state, leaving behind a hole in the sea. This hole would behave like a particle with positive energy and positive charge, the opposite of an electron. Dirac had predicted the existence of antimatter. In 1932, Carl Anderson discovered the positron, the antiparticle of the electron, in cosmic ray experiments, confirming Dirac's prediction. Antimatter is not science fiction. It is a real and fundamental aspect of the universe. Every particle has an antiparticle with the same mass but opposite charge. When a particle and its antiparticle meet, they annihilate, converting their mass into energy according to Einstein's famous equation, E.g.mcc equation, E.g.mcc equation, E.g.mcc equation, E.g.can2, emission tomography, PET scans, and it is studied in particle accelerators around the world. The Dirac equation and the discovery of antimatter reveal the deep connection between quantum mechanics and relativity, and they show that the universe is far richer and stranger than we ever imagined. The quantum vacuum is not a barren void. but a seething ocean of activity. According to the Heisenberg uncertainty principle, energy and time cannot both be precisely known, which means that for sufficiently brief moments, energy can fluctuate wildly. This allows particle-antiparticle pairs to spontaneously emerge from empty space, exist for a fleeting instant, and then annihilate back into nothingness. These are called virtual particles, and though they live for only the tiniest fractions of a second, they have real, measurable effects. Virtual photons mediate electromagnetic forces between charged particles. When two electrons repel each other, they do so by exchanging these ephemeral messengers. Virtual particles also contribute to the Lamb shift and the anomalous magnetic moment of the electron, effects that have been measured with extraordinary precision. The concept of virtual particles challenges our notion of what is real. They cannot be directly observed, yet their influence is undeniable. They remind us that the vacuum is not empty but alive with quantum fluctuations, a background hum of creation and destruction that underlies all of reality. One of the simplest and most important systems in quantum mechanics is the harmonic oscillator, a particle subject to a restoring force proportional to its displacement, like a mass on a spring. In classical physics, such a system can have any energy, depending on how far you stretch the spring. But in quantum mechanics, the energy is quantized, restricted to discrete levels. The lowest energy level, called the ground state, is not zero, but has a finite value known as the zero-point energy. This means that even at absolute zero temperature, when all thermal motion has ceased, the oscillator still vibrates with a minimum quantum jitter. This zero-point energy is a direct consequence of the uncertainty principle. If the particle were perfectly at rest, both its position and momentum would be precisely known, violating the principle. The quantum harmonic oscillator is more than a textbook example. It is a model for many physical systems, from vibrating atoms in a crystal lattice to the modes of the electromagnetic field. Understanding it is essential for describing phonons, photons, and even the behavior of molecules. The zero-point energy has profound implications, contributing to the stability of matter and even to the cosmological constant problem in general relativity. In 1964, physicist John Bell formulated a theorem that would fundamentally challenge our understanding of reality. Bell's theorem addresses the question of whether quantum mechanics is complete, or whether there are hidden variables that determine the outcomes of measurements in advance. Einstein, Podolsky, and Rosen had argued that quantum mechanics must be incomplete because it allowed for entanglement, which seemed to require instantaneous influences across arbitrary distances. Bell derived an inequality that any theory based on local hidden variables must satisfy. He then showed that quantum mechanics predicts violations of this inequality. Experiments, most notably those by Alan Aspect in the 1980s, confirmed that Bell's inequality is indeed violated, ruling out local hidden variable theories. The universe, it seems, is fundamentally non-local. The state of one particle can instantaneously influence the state of another, no matter how far apart they are. This does not allow faster-than-light communication, but it does mean that the universe is more deeply interconnected than classical physics ever imagined. Bell's theorem is one of the most profound results in the foundations of quantum mechanics, demonstrating that the quantum world cannot be explained by any theory that preserves both locality and realism. Quantum mechanics, with all its strangeness, offers practical benefits, and one of the most promising is quantum cryptography. Traditional encryption methods rely on the difficulty of certain mathematical problems, such as factoring large numbers. But these methods are vulnerable to advances in computing power and algorithms. Quantum cryptography, by contrast, is based on the fundamental laws of physics. The most well-known protocol is quantum key distribution, which allows two parties to share a secret encryption key with absolute security. The security comes from the no-cloning theorem, which states that it is impossible to create an identical copy of an unknown quantum state, and from the fact that measuring a quantum system disturbs it. If an eavesdropper tries to intercept the key, their measurement will introduce detectable errors, alerting the legitimate parties to the breach. Quantum key distribution has been demonstrated over fiber optic cables and even via satellite, and commercial systems are already in use. It represents a new paradigm in secure communication, one that is guaranteed by the laws of nature rather than the limits of human ingenuity. Quantum cryptography is a beautiful example of how the abstract principles of quantum mechanics can be harnessed for real-world applications. One of the most fundamental constraints in quantum mechanics is the no-cloning theorem, which states that it is impossible to create an exact copy of an arbitrary unknown quantum state. In classical physics, you can always duplicate an information, copy a book, clone a file, replicate a signal, but in the quantum world, the act of measurement disturbs the system, collapsing the wave function and destroying the original superposition. If you try to measure a quantum state in order to copy it, you inevitably change it, and the information you extract is incomplete. The no-cloning theorem has profound implications. It is the foundation of quantum cryptography, ensuring that eavesdroppers cannot intercept and copy quantum keys without detection. It also places limits on quantum computing and quantum communication, as you cannot simply duplicate quantum information for backup or error correction in the same way you can with classical bits. However, the theorem does not prevent the transfer of quantum information from one system to another, a process called quantum teleportation, which relies on entanglement and classical communication. The no-cloning theorem is a reminder that quantum information is fundamentally different from classical information, obeying different rules and offering different possibilities. Quantum teleportation sounds like science fiction, but it is a real and well-established phenomenon in quantum mechanics. It allows the transfer of a quantum state from one location to another without physically moving the particle itself. The process relies on entanglement and classical communication. Suppose Alice has a qubit in an unknown state and wants to send it to Bob. They share an entangled pair of qubits. Alice performs a joint measurement on her qubit and one half of the entangled pair, which collapses both states and produces a classical result. She sends this result to Bob via a classical channel. Bob then performs an operation on his half of the entangled pair, conditioned on Alice's measurement result, which transforms his qubit into the original state that Alice had. The original qubit is destroyed in the process, so no cloning occurs, and the no-cloning theorem is preserved. Quantum teleportation does not allow faster-than-light communication, as the classical information must still be transmitted. But it does enable the transfer of quantum information across distances. It has been demonstrated experimentally with photons, atoms, and even small ensembles of particles. And it is a key component of proposed quantum communication networks and quantum computers. At the heart of quantum mechanics lies the Schrödinger equation, a mathematical expression that describes how the wave function of a quantum system evolves over time. Proposed by Erwin Schrödinger in 1926, the equation is deterministic. Given the wave function at one moment, you can calculate it at any future moment. but the wave function itself is probabilistic, encoding not definite outcomes but probability. The Schrödinger equation is a partial differential equation, and solving it for different systems reveals the allowed energy levels, the shapes of orbitals, and the dynamics of quantum processes. For the hydrogen atom, it predicts the discrete energy levels that electrons can occupy. For a particle in a box, it shows that only certain wavelengths fit, leading to quantized energies. The equation is linear, which means that if two states are solutions, their superposition is also a solution, a property that underlies much of quantum weirdness. The Schrödinger equation is to quantum mechanics what Newton's laws are to classical mechanics, a foundational principle from which countless phenomena can be derived. It is a testament to the power of mathematics to describe the physical world, revealing the hidden order beneath the apparent randomness of quantum events. One of the deepest and most contentious issues in quantum mechanics is the measurement problem. According to the Schrödinger equation, a quantum system evolves smoothly and deterministically, existing in a superposition of states. But when a measurement is made, the superposition collapses, and the system assumes a definite state. This collapse is sudden, discontinuous, and seemingly random, governed only by probabilities. The measurement problem asks, what constitutes a measurement, and what causes the collapse? Is it the interaction with a macroscopic apparatus, the involvement of a conscious observer, or something else? Different interpretations of quantum mechanics offer different answers. A Copenhagen interpretation treats measurement as a fundamental process, but does not specify what counts as a measurement. The many worlds interpretation denies that collapse occurs at all, proposing instead that all possible outcomes happen in branching parallel universes. The pilot wave theory introduces hidden variables that guide particles along definite trajectories. Decoherence offers a partial answer, explaining how interaction with the environment causes the appearance of collapse, but it does not explain why a particular outcome is selected. The measurement problem remains unsolved. A reminder that despite its extraordinary success, quantum mechanics is not yet fully understood. Classical computers process information using bits, which can be either 0 or 1. Quantum computers use qubits, which can exist in a superposition of 0 and 1 simultaneously. This allows a quantum computer to explore many possibilities at once, potentially solving certain problems exponentially faster than classical computers. A qubit can be realized using various physical systems, such as the spin of an electron, the polarization of a photon, or the energy levels of an atom. When qubits are entangled, the state of the entire system cannot be described by the states of individual qubits. They form a collective quantum state. This entanglement is a resource that quantum algorithms exploit. For example, Shor's algorithm can factor large numbers efficiently, threatening current encryption methods, while Grover's algorithm can search unsorted databases quadratically faster than classical algorithms. However, building a practical quantum computer is extraordinarily challenging. Qubits are fragile and susceptible to decoherence, which destroys the quantum information. Researchers are developing error correction techniques and exploring different qubit technologies to overcome these obstacles. Quantum computing is still in its infancy, but it promises to revolutionize fields from cryptography to drug discovery to optimization. In classical electromagnetism, charged particles are affected by electric and magnetic fields, which are measurable quantities. But in quantum mechanics, the fundamental entities are not the fields, but the potentials from which the fields are derived. The Aharonov-Bohm effect, predicted in 1959 and confirmed experimentally, demonstrates this in a striking way. Imagine an electron beam split into two paths that encircle a solenoid, a coil of wire carrying a current. The solenoid produces a magnetic field confined to its interior, so the electrons traveling outside experience no magnetic field. Classically, they should be unaffected, but quantum mechanically, the electrons are influenced by the magnetic vector potential, which exists even in regions where the magnetic field is zero. This causes a phase shift in the electron wave function, leading to an observable interference pattern when the beams recombine. The Aharonov-Bohm effect shows that potentials, not just fields, have physical significance in quantum mechanics. It also illustrates the non-local nature of quantum mechanics, as the electrons are affected by a field they never directly encounter. The effect has been confirmed in numerous experiments and has deepened our understanding of the relationship between classical and quantum descriptions of electromagnetism. Quantum dots are nanoscale semiconductor particles, typically just a few nanometers across, small enough that quantum effects dominate their behavior. In bulk semiconductors, electrons can occupy a continuous range of energies within bands. But in a quantum dot, the electrons are confined to a tiny region, and their energy levels become discrete, much like electrons in an atom. For this reason, quantum dots are sometimes called artificial atoms. The energy levels, and thus the color of light the quantum dot emits or absorbs, depend on the size of the dot. Smaller dots have larger energy gaps and emit bluer light. This tunability makes quantum dots incredibly useful. They are used in displays where they produce vivid, pure colors. They are employed in biological imaging, where they can tag specific molecules and be tracked inside living cells. They are being explored for use in solar cells, where their tunable absorption can be optimized to capture more of the solar spectrum, and in quantum computing, where they can serve as qubits. Quantum dots are a beautiful example of how quantum mechanics, once the domain of abstract theory, has become a tool for engineering new materials and technologies, with properties tailored at the atomic level. In 1980, Klaus von Klitzing discovered the quantum Hall effect. While studying the behavior of electrons in a two-dimensional conductor subjected to a strong magnetic field at low temperatures, he found that the Hall resistance, a measure of the voltage developed perpendicular to the current, was quantized, taking on values that were precise, integer multiples of a fundamental constant. This quantization was extraordinarily accurate, independent of the material or the details of the sample, and it provided a new standard for electrical resistance. The quantum Hall effect arises from the formation of Landau levels, discrete energy levels that electrons occupy in a magnetic field, combined with the topology of the electron wave functions. Later, the fractional quantum Hall effect was discovered, where the resistance is quantized at fractional values, a phenomenon that can only be explained by the collective behavior of electrons forming exotic quasiparticles with fractional charge. The quantum Hall effect has deep connections to topology, a branch of mathematics, and it has led to the discovery of new states of matter called topological insulators. It is a prime example of how quantum mechanics can produce macroscopic phenomena with extraordinary precision, and it has practical applications in metrology, providing a universal standard for resistance. Quantum annealing is a computational technique that exploits quantum mechanics to find the lowest energy state of a system, which corresponds to the solution of an optimization problem. Classical optimization algorithms can get stuck in local minima, suboptimal solutions that are better than their immediate neighbors but not the global best. Quantum annealing uses quantum tunneling to escape these local minima, allowing the system to explore the energy landscape more effectively. The process begins with the system in a superposition of all possible states. A time-dependent Hamiltonian is applied, gradually transforming the system from an initial simple state to a final state whose ground state encodes the solution to the problem. If the transformation is slow enough, the system remains in the ground state throughout, a principle known as adiabatic evolution. Quantum annealers, such as those built by D-Wave Systems, have been used to tackle problems in machine learning, logistics, and material science. However, whether they offer a true quantum speed-up over classical methods is still a subject of research and debate. Quantum annealing represents a different approach to quantum computing, one that is specialized for optimization rather than general-purpose computation, and it highlights the diverse ways quantum mechanics can be harnessed for practical problem-solving. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper challenging the completeness of quantum mechanics. They devised a thought experiment involving two entangled particles. According to quantum mechanics, measuring one particle instantaneously determines the state of the other, regardless of the distance separating them. Einstein found this deeply troubling, calling it spooky action at a distance. He argued that this implied either faster-than-light influences which violated relativity, or that quantum mechanics was incomplete and there existed hidden variables that predetermined the measurement outcomes. The EPR paradox was intended to demonstrate that quantum mechanics could not be the final word on reality. For decades, the debate remained philosophical as the predictions of quantum mechanics and hidden variable theories seemed indistinguishable. But in 1964, John Bell showed that the two approaches made different predictions for certain experiments, and subsequent tests have consistently confirmed quantum mechanics. The EPR paradox, rather than undermining quantum theory, ultimately strengthened it, demonstrating that the universe is fundamentally non-local and that entanglement is a real physical phenomenon. Einstein's discomfort with quantum mechanics reflects the profound challenge it poses to our classical intuitions about reality, locality, and causality. Quantum mechanics is often thought of as relevant only to the microscopic world of atoms and subatomic particles, but recent research suggests that quantum effects may play a role in biological processes. One of the most striking examples is photosynthesis, the process by which plants convert sunlight into chemical energy. When a photon is absorbed by a light harvesting complex, it creates an exciton, a quantum of energy that must be transferred to a reaction center where it can be used. Experiments have shown that this energy transfer is remarkably efficient, far more so than classical models predict. The explanation appears to involve quantum coherence. The exciton exists in a superposition of multiple pathways simultaneously, allowing it to explore all routes and find the most efficient one. This quantum effect persists even at the warm, noisy conditions inside a living cell, where decoherence would normally destroy such delicate states. Other potential quantum effects in biology include the sense of smell, where the shape and vibrational frequency of molecules may be detected quantum mechanically, and avian navigation, where birds may use entangled electron pairs in their eyes to sense the Earth's magnetic field. These discoveries suggest that life has learned to harness quantum mechanics, using it to achieve efficiencies and capabilities that would be impossible classically. In 1948, Dutch physicist Hendrik Casimir predicted a strange consequence of quantum field theory. Two uncharged, parallel metal plates placed very close together in a vacuum should experience an attractive force. This seems paradoxical as there is nothing between the plates to push them together. The explanation lies in the quantum vacuum. Even in the absence of particles, Quantum fields undergo fluctuations, with virtual particle pairs constantly appearing and disappearing. These fluctuations have different wavelengths, and between the plates, only certain wavelengths fit. While outside the plates, all wavelengths are allowed. This creates a difference in the vacuum energy density, resulting in a net pressure that pushes the plates together. The Casimir effect was experimentally confirmed in 1958 and has since been measured with increasing precision. It is a direct demonstration that the vacuum is not empty but filled with quantum activity. The effect is tiny, significant only at very small distances, but it has practical implications for nanotechnology, where it can cause unwanted sticking between components. The Casimir effect also provides a window into the nature of the vacuum and has connections to cosmology, where vacuum energy may be related to dark energy. It is a beautiful example of how abstract quantum predictions can manifest as measurable physical forces. One of the greatest challenges in building a quantum computer is protecting quantum information from errors. Qubits are fragile, easily disturbed by their environment, and decoherence can destroy the quantum state in a fraction of a second. Classical error correction relies on redundancy. You make multiple copies of a bit, and if one is corrupted, you can recover the original by majority vote. But in quantum mechanics, the no-cloning theorem forbids making exact copies of an unknown quantum state. How, then, can quantum information be protected? The answer is quantum error correction, a set of techniques that encode a single logical qubit into multiple physical qubits in such a way that errors can be detected and corrected without measuring the quantum state directly. The simplest example is the 3-qubit bit flip code, which protects against a qubit flipping from 0 to 1 or vice versa. More sophisticated codes such as the Shaw code and the surface code can protect against multiple types of errors simultaneously. Quantum error correction is essential for building large-scale fault-tolerant quantum computers. It allows quantum information to be preserved and manipulated reliably, even in the presence of noise and imperfections. The development of efficient error correction codes is one of the most active areas of research in quantum computing. Heisenberg's uncertainty principle is most commonly stated in terms of position and momentum. The more precisely you know one, the less precisely you can know the other. But there is another form of the principle involving energy and time. It states that the uncertainty in energy multiplied by the uncertainty in time is at least as large as Planck's constant divided by 4. This has profound implications. For a quantum state that exists for only a short time, the uncertainty in its energy must be large. This is why virtual particles, which exist for only fleeting moments, can have energies that violate energy conservation as long as they disappear quickly enough. The energy-time uncertainty principle also explains the natural line width of spectral lines. When an atom transitions from an excited state to a lower energy state, it emits a photon. The excited state has a finite lifetime, and the uncertainty in this lifetime leads to an uncertainty in the energy of the emitted photon, broadening the spectral line. The principle sets fundamental limits on measurement and timekeeping. It means that there is a trade-off between how quickly you can measure something and how accurately you can determine its energy. The energy-time uncertainty principle is a reminder that time, like position and momentum, is subject to quantum limitations. Entanglement is already strange, but quantum mechanics allows for even more counterintuitive phenomena, such as entanglement swapping. Imagine two pairs of entangled particles. Alice has one particle from the first pair, Bob has one from the second pair, and the remaining two particles are held by a third party, Charlie. If Charlie performs a joint measurement on his two particles, Alice's and Bob's particles, which have never interacted, become entangled. The entanglement is transferred, or swapped, from the original pairs to a new pair. This process does not require Alice and Bob to be in the same location or to have any direct interaction. Entanglement swapping has been demonstrated experimentally and is a key component of quantum repeaters, devices that extend the range of quantum communication by creating entanglement over long distances in a step-by-step fashion. It also plays a role in quantum teleportation networks, where entanglement is distributed among multiple parties. Entanglement swapping highlights the non-local nature of quantum mechanics and the fact that entanglement is a resource that can be manipulated and transferred, much like classical information, but with fundamentally different properties. The double-slit experiment demonstrates that observing which slit a particle passes through destroys the interference pattern. But what if you could erase the information about which path the particle took after the fact? The quantum eraser experiment shows that this is possible. In one version, photons are sent through a double-slit apparatus, and their paths are marked by entangling them with other photons. If you measure the marking photons to determine which slit the original photon passed through, the interference pattern disappears. But if you perform a different measurement on the marking photons, one that erases the which path information, the interference pattern reappears. Remarkably, you can even delay the choice of measurement until after the original photon has been detected. This does not allow retrocausal signaling or time travel, as the interference pattern only becomes apparent when you correlate the results of both measurements. The quantum eraser demonstrates the subtlety of the measurement process in quantum mechanics and the role of information. It shows that what matters is not whether the information exists in principle, but whether it is accessible. The experiment challenges our intuitions about causality and the flow of time, revealing the deep strangeness of the quantum world. Most approaches to quantum computing use qubits that are encoded in the states of individual particles, such as the spin of an electron or the polarization of a photon. But there is another approach, called topological quantum computing, that encodes information in the global properties of a system, properties that are robust against local disturbances. The idea is to use quasiparticles called anyons, which exist in certain two-dimensional systems and have exotic statistical properties. When anyons are braided around each other, their quantum state changes in a way that depends only on the topology of the braiding, not on the precise path taken. This makes the information stored in the braiding inherently protected from errors caused by small perturbations. Topological quantum computing is still largely theoretical, but it holds great promise for building fault-tolerant quantum computers. Microsoft and other companies are investing heavily in developing topological qubits, and there have been experimental hints of anyonic behavior in certain materials. If successful, topological quantum computing could overcome one of the greatest obstacles to practical quantum computation: the fragility of quantum information. Some quantum systems are so complex that even the most powerful classical computers cannot simulate them. The number of variables grows exponentially with the size of the system, quickly overwhelming any classical approach. But a quantum computer, which itself operates according to quantum mechanics, can naturally simulate other quantum systems. This idea, proposed by Richard Feynman in the 1980s, is one of the most promising applications of quantum computing. Quantum simulators can model the behavior of molecules, materials, and fundamental particles, providing insights into chemistry, condensed matter physics, and high-energy physics. For example, they can be used to design new drugs by simulating how molecules interact to discover new materials with desired properties like superconductivity, or to understand the behavior of quarks and gluons in extreme conditions. Quantum simulators can be analog, where a controllable quantum system is tuned to mimic the system of interest, or digital, where a universal quantum computer runs an algorithm to simulate the system. Both approaches are being actively developed, and quantum simulation is expected to be one of the first areas where quantum computers provide a clear advantage over classical methods. The quantum Zeno effect, named after the ancient Greek philosopher, states that frequent measurements can freeze the evolution of a quantum system. But there is a related phenomenon, sometimes called the quantum anti-Zeno effect, where frequent measurements can actually accelerate the decay of a system. Whether the Zeno or anti-Zeno effect occurs depends on the details of the measurement and the system's environment. If the measurements are spaced at intervals shorter than the natural timescale of the system's evolution, the Zeno effect dominates, and the system is effectively frozen. If the intervals are longer, the anti-Zeno effect can take over, and the system decays more rapidly than it would without measurement. These effects have been observed experimentally and have implications for quantum control and quantum information processing. They demonstrate the profound role that measurement plays in quantum mechanics, not just as a passive observation, but as an active intervention that can either preserve or destroy quantum states. The quantum Zeno paradox is a reminder that in the quantum realm, the act of watching is never neutral. Quantum mechanics imposes fundamental limits on measurement precision, but it also provides tools to approach those limits and even surpass classical methods. Quantum metrology is the science of using quantum effects to make ultra-precise measurements. One key resource is entanglement. In classical metrology, the precision of a measurement improves with the square root of the number of measurements or particles used. But with entangled states, the precision can improve linearly with the number of particles, a phenomenon known as the Heisenberg limit. This has applications in atomic clocks, which use the quantum states of atoms to measure time with extraordinary accuracy, and in gravitational wave detectors, which use squeezed light, a quantum state with reduced noise in one variable at the expense of increased noise in another. To improve sensitivity, quantum metrology is also being explored for applications in navigation, imaging, and sensing. By harnessing quantum effects, scientists can measure quantities like magnetic fields, gravitational fields, and time with a precision that would be impossible classically, opening new frontiers in fundamental physics and practical technology. The quantum approximate optimization algorithm, or QAOA, is a quantum algorithm designed to solve combinatorial optimization problems, where the goal is to find the best solution from a finite set of possibilities. Examples include the traveling salesman problem, where you want to find the shortest route visiting a set of cities, and the maximum cut problem, where you want to partition a graph to maximize the number of edges between partitions. QAO works by preparing a quantum state that encodes the problem, then applying a sequence of quantum operations that gradually evolve the state toward the optimal solution. The algorithm is approximate, meaning it does not guarantee the exact optimal solution, but it can find good solutions efficiently. QAOA is particularly well suited to near-term quantum computers, which have limited qubits and are prone to errors, because it can be implemented with relatively shallow circuits. Researchers are exploring its performance on various problems and comparing it to classical algorithms. QAOA represents a promising approach to harnessing the power of quantum computing for practical optimization tasks, with potential applications in logistics, finance, and machine learning. Quantum coherence refers to the ability of a quantum system to exist in a superposition of states with well-defined phase relationships. It is coherence that allows for interference effects, where different components of the superposition can constructively or destructively interfere. Coherence is fragile, easily destroyed by interaction with the environment. A process called decoherence. When a quantum system interacts with its surroundings, it becomes entangled with a vast number of environmental degrees of freedom, and the phase relationships that define coherence are scrambled. The system transitions from a pure quantum state to a mixed state, a statistical ensemble that behaves classically. Decoherence is the primary obstacle to building quantum computers and maintaining quantum effects in macroscopic systems. It sets a timescale, the coherence time, within which quantum operations must be performed. Researchers are developing techniques to extend coherence times, such as isolating qubits from their environment, using error correction, and designing systems that are inherently less susceptible to decoherence. Understanding coherence and decoherence is essential for bridging the quantum and classical worlds, and for harnessing quantum mechanics in technology. Entanglement is often described as a correlation between particles, but it is more accurately understood as a form of quantum information. When two particles are entangled, the information about the system is not contained in either particle individually but in the relationship between them. This has profound implications for how we think about information and reality. In classical physics, information is local. It resides in specific objects or locations, but in quantum mechanics, information can be non-local, distributed across entangled particles in a way that cannot be reduced to the properties of individual components. This non-local information is what allows for phenomena like quantum teleportation and quantum cryptography. It also raises deep questions about the nature of information itself. Is information physical, or is it abstract? Does it have mass or energy? Quantum mechanics suggests that information is a fundamental aspect of reality, perhaps even more fundamental than matter or energy. The study of quantum information has given rise to a new field, quantum information theory, which explores the limits of information processing, the nature of entropy, and the connections between information, thermodynamics, and gravity. Entanglement reveals that the universe is woven together by invisible threads of information, connecting distant regions in ways that defy classical understanding. The delayed choice experiment, proposed by John Wheeler, is a variation of the double-slit experiment that challenges our notions of causality and the role of observation. In the standard double-slit experiment, you decide in advance whether to observe which slit the particle passes through. But in the delayed choice version, you make that decision after the particle has already passed through the slits, but before it is detected. If you choose to observe which path the particle took, it behaves like a particle, passing through one slit. If you choose not to observe, it behaves like a wave, passing through both slits and creating an interference pattern. The remarkable thing is that the particle seems to know what measurement you will make, even though that decision is made after it has already committed to a path. This does not imply backward causation or time travel. Rather, it demonstrates that the particle does not have a definite path until a measurement is made. The delayed choice experiment has been performed with photons, atoms, and even large molecules, and the results consistently confirm the predictions of quantum mechanics. It underscores the fact that quantum mechanics is fundamentally about information and measurement, not about particles following predetermined trajectories through space and time. In classical physics, the properties of an object exist independently of how you measure them. A ball has a definite color, size, and mass, whether you look at it or not. But in quantum mechanics, the situation is more subtle. Quantum contextuality refers to the fact that the outcome of a measurement can depend on what other measurements are made alongside it. The properties of a quantum system are not pre-existing, but emerge in the context of measurement. This was demonstrated by the Cauchy-Becker theorem, which shows that it is impossible to assign definite values to all observables of a quantum system in a way that is consistent with the predictions of quantum mechanics. The theorem rules out non-contextual hidden variable theories, where measurement outcomes are determined by pre-existing properties. Contextuality has been confirmed experimentally and is considered a fundamental feature of quantum mechanics, distinct from entanglement. It has implications for quantum computing, as contextuality is a resource that can be exploited for computational advantage. It also deepens the mystery of quantum measurement, showing that the act of observation does not merely reveal pre-existing properties, but actively participates in creating the reality we observe. Quantum mechanics tells us that the state of a system is a superposition of possibilities until a measurement is made. But in everyday life, we observe definite, objective outcomes. How does the quantum world give rise to the classical world we experience? Quantum Darwinism, proposed by Wojciech Jurek, offers an answer. The idea is that certain states of a quantum system are more robust and are preferentially imprinted onto the environment. When a quantum system interacts with its environment, information about the system is redundantly copied into many environmental degrees of freedom, such as photons, air molecules, and other particles. These copies are like fossils, records of the system's state that can be independently accessed by multiple observers. The states that survive this process are the ones that are most stable and least disturbed by the environment. The classical states. This process is analogous to natural selection, where the fittest states survive and proliferate. Quantum Darwinism explains why we all agree on the outcome of a measurement and why the world appears classical at macroscopic scales. It shows that objectivity emerges from the quantum substrate through a process of environmental selection, bridging the gap between the quantum and classical realms. In classical physics, there is no fundamental limit to how quickly a system can change from one state to another, given enough energy. But in quantum mechanics, there is a speed limit, known as the quantum speed limit, which bounds how fast a quantum state can evolve. This limit is related to the energy of the system and the uncertainty principle. The quantum speed limit has implications for quantum computing, as it sets a fundamental bound on how quickly quantum gates can operate and how fast quantum algorithms can run. It also has connections to thermodynamics and the arrow of time, as the speed of evolution is related to entropy production. Researchers have derived various forms of the quantum speed limit for different types of systems and processes, and experiments have tested these limits in controlled quantum systems. The quantum speed limit is a reminder that even in the quantum world, where so much seems strange and counterintuitive, there are fundamental constraints imposed by the laws of physics. It shows that speed, like position and momentum, is subject to quantum limitations, and that the universe operates according to deep, universal principles. A random walk is a mathematical model where a particle takes steps in random directions, used to describe processes like diffusion and Brownian motion. A quantum walk is the quantum analog, where a particle exists in a superposition of positions and moves according to quantum rules. Unlike a classical random walk, which spreads out slowly, a quantum walk can spread much faster, exploring a larger region of space in the same amount of time. This is because the particle explores multiple paths simultaneously, and interference between these paths can lead to constructive buildup in certain regions. quantum walks have applications in quantum algorithms, where they can be used to search databases, solve graph problems, and simulate physical systems more efficiently than classical methods. They also provide insights into quantum transport phenomena, such as energy transfer in photosynthesis and electron transport in materials. Quantum walks have been experimentally realized using photons, atoms, and trapped ions, and they are being explored as a tool for quantum computing and quantum simulation. The quantum walk is a beautiful example of how quantum superposition and interference can lead to fundamentally different behavior than classical processes, offering new ways to solve problems and understand nature. The pigeonhole principle is a simple classical idea. If you have more pigeons than pigeonholes, at least one pigeonhole must contain more than one pigeon. But in quantum mechanics, this principle can be violated. In 2014, researchers demonstrated a quantum pigeonhole effect, where 3 particles were placed in 2 boxes, yet no box contained more than 1 particle. This paradox arises because of quantum measurements. The particles do not have definite locations until measured, and the outcome depends on how you choose to measure. By carefully designing the measurement, you can create a situation where the classical pigeonhole principle does not hold. The quantum pigeonhole principle is not just a curiosity. It highlights the fundamental differences between classical and quantum logic. It shows that the rules of reasoning we take for granted in everyday life do not apply in the quantum realm. This has implications for quantum computing and quantum information, where exploiting these non-classical features can lead to new computational capabilities. The quantum pigeonhole principle is a reminder that quantum mechanics is not just a modification of classical physics, but a radically different framework for understanding reality. Energy storage is a critical challenge for modern technology, and quantum mechanics may offer new solutions. Quantum batteries are devices that use quantum effects to store and release energy more efficiently than classical batteries. The key idea is to exploit quantum coherence and entanglement to enhance the charging process. In a classical battery, energy is stored in individual cells, and the charging time scales linearly with the number of cells. But in a quantum battery, if the cells are entangled, they can be charged collectively, and the charging time can scale much more favorably, potentially as the square root of the number of cells or even faster. This is known as quantum speedup. Quantum batteries are still largely theoretical, but researchers are exploring various physical implementations, such as using arrays of qubits or quantum harmonic oscillators. The challenges include maintaining coherence during the charging and discharging process, and scaling up to practical sizes. Quantum batteries could have applications in portable electronics, electric vehicles, and grid-scale energy storage, offering faster charging times and higher energy densities. They represent a frontier where quantum mechanics meets practical engineering, with the potential to revolutionize how we store and use energy. In Lewis Carroll's Alice's Adventures in Wonderland, the Cheshire Cat can disappear, leaving only its grin behind. In quantum mechanics, a similar phenomenon can occur, where a property of a particle can be separated from the particle itself. This is known as the quantum Cheshire Cat effect. In experiments, researchers have used weak measurements, a technique that extracts only a small amount of information without fully collapsing the wave function, to show that a neutron's self is in another. This separation is not absolute but statistical, emerging from the peculiarities of quantum measurement and interference. The quantum Cheshire Cat effect challenges our intuition that properties are intrinsic to objects and always accompany them. It demonstrates the contextual and relational nature of quantum properties, where what you observe depends on how you measure. The effect has been experimentally verified and has implications for understanding the nature of quantum measurement and the relationship between particles and their properties. It is a whimsical yet profound illustration of the quantum world. Thermodynamics, the study of heat, work, and dynamics. The study of heat, work, and dynamics entry to understand steam engines and other macroscopic systems. But what happens when you apply thermodynamic concepts to quantum systems where individual particles and quantum fluctuations matter? Quantum thermodynamics explores this question, examining how the laws of thermodynamics are modified at the quantum scale. One key insight is that quantum coherence and entanglement can be resources, much like energy, that can be used to perform work or extract heat. For example, a quantum engine can exploit coherence to achieve efficiencies that exceed classical limits. Quantum thermodynamics also addresses the role of information and measurement, building on the work of Maxwell's demon, a thought experiment where information is used to violate the second law of thermodynamics. In the quantum version, the demon must account for the quantum nature of information and the cost of measurement and erasure. Quantum thermodynamics has applications in understanding nanoscale devices, quantum computers, and even biological systems. It reveals that the boundary between thermodynamics and information theory is blurred at the quantum level, and that energy, entropy, and information are deeply intertwined. Quantum mechanics provides tools for sensing and measuring physical quantities with unprecedented precision. Quantum sensors exploit effects like superposition, entanglement, and squeezing to achieve sensitivities beyond classical limits. One example is the atomic magnetometer, which uses the quantum states of atoms to detect magnetic fields with extraordinary accuracy, useful for applications ranging from medical imaging to mineral exploration. Another is the nitrogen vacancy center in diamond, a defect in the crystal lattice that can be used as a quantum sensor for magnetic fields, temperature, and pressure at the nanoscale. Quantum sensors are also being developed for gravitational wave detection, where squeezed light reduces noise and improves sensitivity, and for inertial navigation, where atom interferometry measures acceleration and rotation with high precision. Quantum sensing is a rapidly growing field, with applications in fundamental physics, geophysics, biology, and defense. Dialogy and defense. It demonstrates that the strange features of quantum mechanics, once thought to be mere curiosities, can be harnessed for practical purposes, providing new ways to probe the world around us. The Monty Hall problem is a famous probability puzzle based on a game show. You choose one of 3 doors, behind one of which is a prize. After you choose, the host, who knows what's behind the doors, opens one of the other doors to reveal no prize. You are then given the option to switch your choice. Classical probability shows that switching doubles your chances of winning. But in the quantum version of the problem, the rules change. If the doors are in a quantum superposition and the host's action is a quantum measurement, the probabilities can be different. Researchers have analyzed the quantum Monty Hall problem and found that depending on the quantum state and the measurement strategy, the advantage of switching can be greater or less than in the classical case. The quantum version highlights how quantum superposition and entanglement affect decision-making and probability. It also serves as a pedagogical tool for understanding quantum measurement and the differences between classical and quantum reasoning. The quantum Monty Hall problem is a playful yet instructive example of how quantum mechanics can alter even the most familiar scenarios. Reservoir computing is a machine learning approach where a fixed, randomly connected network called a reservoir processes input signals and only the output layer is trained. The reservoir acts as a rich, nonlinear transformation of the input, making it easier to learn complex patterns. Quantum reservoir computing extends this idea to the quantum realm, using a quantum system as the reservoir. The quantum reservoir can exploit superposition and entanglement to create a high-dimensional state space, potentially offering advantages over classical reservoirs. Quantum reservoir computing has been demonstrated experimentally using photonic systems, superconducting qubits, and atomic ensembles. It is particularly attractive for near-term quantum devices, as it does not require full quantum control or error correction. Applications include time series prediction, pattern recognition, and solving differential equations. Quantum reservoir computing represents a hybrid approach, combining the strengths of quantum and classical computing, and it is part of a broader effort to find practical uses for noisy, intermediate-scale quantum devices. It shows that even without a fully fault-tolerant quantum computer, quantum effects can enhance machine learning and information processing. Quantum non-locality is one of the most profound and counterintuitive features of quantum mechanics. It refers to the fact that entangled particles exhibit correlations that cannot be explained by any local theory, where influences are limited to the speed of light. When two particles are entangled, measuring one instantaneously affects the state of the other, regardless of the distance separating them. This was demonstrated conclusively by experiments testing Bell's inequalities, which showed that the correlations predicted by quantum mechanics are stronger than any local hidden variable theory could produce. Non-locality does not allow faster-than-light communication, as the measurement outcomes are random and only reveal their correlation when compared. Yet it implies that the universe is fundamentally interconnected in ways that transcend space and time. Quantum non-locality has been verified over distances ranging from meters to hundreds of kilometers, and even between Earth and satellites in orbit. It challenges our deepest intuitions about the separability of objects and the independence of distant events. Non-locality is not a bug in quantum mechanics, but a feature revealing that reality is woven from relationships and correlations that cannot be reduced to local properties. It is a window into the holistic nature of the quantum world. The Fourier transform is a mathematical operation that decomposes a signal into its constituent frequencies, widely used in signal processing, image analysis, and many other fields. The quantum Fourier transform is the quantum analog, operating on quantum states rather than classical signals. It is a key component of many quantum algorithms, most notably Shor's algorithm for factoring large numbers. The quantum Fourier transform can be implemented efficiently on a quantum computer, requiring only a polynomial number of quantum gates, whereas the classical Fourier transform requires exponentially many operations for certain tasks. This efficiency arises from the ability of quantum computers to process superpositions of states in parallel. The quantum Fourier transform has applications beyond factoring, including quantum phase estimation, solving systems of linear equations, and simulating quantum systems. It is a powerful tool that leverages the unique properties of quantum mechanics to perform computations that would be intractable classically. The quantum Fourier transform exemplifies how quantum algorithms can exploit superposition and interference to achieve exponential speedups, opening new possibilities for computation and problem solving. Quantum supremacy, also called quantum advantage, refers to the point at which a quantum computer can perform a calculation that is practically impossible for any classical computer, no matter how powerful. In 2019, Google announced that its quantum processor Sycamore had achieved quantum supremacy by performing a specific task in 200 seconds that would take the world's most powerful supercomputer thousands of years. The task was a contrived one, designed to be hard for classical computers, but easy for quantum computers, and it had no immediate practical application. Nevertheless, it was a milestone, demonstrating that quantum computers can outperform classical computers in certain domains. Quantum supremacy is not the end goal, but a stepping stone toward building quantum computers that can solve useful problems, such as simulating molecules for drug discovery, optimizing logistics, or breaking encryption. Achieving quantum supremacy requires not only building a quantum processor with enough qubits, but also maintaining coherence and minimizing errors. It is a testament to the progress in quantum computing holds. Quantum key distribution, or QKD, is a method for securely sharing encryption keys using the principles of quantum mechanics. The most well-known protocol is BB84, developed by Charles Bennett and Gilles Brassard in 1984. In BB84, the sender encodes bits of information in the quantum states of photons, such as their polarization, and sends them to the receiver. The receiver measures the photons, and the sender and receiver compare a subset of their results over a public channel to check for eavesdropping. If an eavesdropper tries to intercept the photons, the act of measurement will disturb the quantum states, introducing detectable errors. Once the sender and receiver are confident that the key is secure, they can use it to encrypt and decrypt messages. QKD has been demonstrated over fiber optic cables spanning hundreds of kilometers and via satellite links, enabling secure communication over global distances. It is already being deployed in commercial systems for banking, government, and critical infrastructure. Quantum key distribution represents a paradigm shift in cryptography, offering security guaranteed by the laws of physics rather than the computational difficulty of mathematical problems. It is a practical application of quantum mechanics that is already changing how we protect information. The quantum Rabi model describes the interaction between a two-level quantum system, such as an atom, and a quantized electromagnetic field, such as a photon in a cavity. It is one of the simplest and most fundamental models in quantum optics, capturing the essential physics of light-matter interaction. The model predicts phenomena such as Rabi oscillations, where the atom periodically absorbs and emits photons, transitioning between its ground and excited states. The frequency of these oscillations depends on the strength of the coupling between the atom and the field. The quantum Rabi model is exactly solvable in certain limits and has been used to understand a wide range of phenomena, from laser operation to quantum information processing. It also serves as a testing ground for more complex models and as a platform for exploring fundamental questions about quantum mechanics. Experiments with trapped ions, superconducting circuits, and other systems have realized the quantum Rabi model and verified its predictions. The model is a cornerstone of quantum optics and a beautiful example of how a simple theoretical framework can illuminate the behavior of complex quantum systems. Machine learning, the science of teaching computers to learn from data, has transformed fields from image recognition to natural language processing. Quantum machine learning explores how quantum computers can enhance or accelerate machine learning tasks. Quantum computers can process high-dimensional data in superposition, potentially offering speed-ups for tasks like classification, clustering, and optimization. Quantum algorithms have been proposed for principal component analysis, support vector machines, and neural network training. Some of these algorithms promise exponential speedups, though the conditions under which these speedups are realized are still being explored. quantum machine learning also includes using machine learning to control and optimize quantum systems, such as designing quantum gates or correcting errors. The field is still in its early stages, with many open questions about where quantum advantages will be most significant. Quantum machine learning represents a convergence of two of the most exciting frontiers in technology, and it holds the promise of new capabilities for artificial intelligence and data science. The quantum Zeno effect, where frequent measurements freeze the evolution of a quantum system, can be harnessed to perform quantum operations. A quantum Zeno gate uses repeated measurements to selectively suppress certain transitions while allowing others, effectively steering the system into a desired state. This approach can be used to implement quantum gates without the need for precise control pulses, relying instead on the measurement-induced dynamics. Quantum Zeno gates have been demonstrated experimentally and are being explored as a tool for quantum computing and quantum control. They offer a different paradigm for manipulating quantum systems, one that exploits the peculiarities of quantum measurement rather than fighting against them. The quantum Zeno gate is an example of how the strange features of quantum mechanics can be turned into practical resources, transforming what might seem like an obstacle into an opportunity. Quantum illumination is a technique for detecting objects in noisy environments using entangled photons. In a typical radar or LiDAR system, a signal is sent out, and the reflected signal is detected. But in noisy environments, the signal can be overwhelmed by background noise. Quantum illumination uses entangled pairs of photons. One photon is sent toward the target, and the other is kept as a reference. Even if the signal photon is heavily degraded by noise, the entanglement between the signal and reference photons provides a correlation that can be exploited to detect the target more effectively than classical methods. Quantum illumination does not require the entanglement to survive the round trip. The advantage comes from the initial correlation. The technique has been demonstrated experimentally and has potential applications in remote sensing, medical imaging, and security. Quantum illumination is a striking example of how entanglement, even when partially destroyed, can provide advantages over classical approaches. The quantum internet is a proposed network that uses quantum signals to transmit information, enabling applications that are impossible with classical communication. Unlike the classical internet, which transmits bits, the quantum internet would transmit qubits, allowing for quantum key distribution, distributed quantum computing, and quantum sensing over long distances. The quantum internet would rely on quantum repeaters, devices that use entanglement swapping and quantum error correction to extend the range of quantum communication beyond the limits imposed by photon loss in optical fibers. Building a quantum internet is a major engineering challenge, requiring advances in quantum memory, entanglement generation, and integration with existing infrastructure. Several countries and organizations are investing in quantum internet research, and prototype networks have been demonstrated in laboratories and between cities. The quantum internet promises to revolutionize secure communication, enable new forms of distributed computation, and connect quantum sensors and computers into a global network. It represents the next frontier in networking, where the strange rules of quantum mechanics become the foundation for a new kind of connectivity. Quantum optomechanics is the study of the interaction between light and mechanical motion at the quantum level. It involves coupling optical fields, such as laser light in a cavity, to mechanical oscillators such as vibrating mirrors or membranes. When the coupling is strong enough, quantum effects become important, and the mechanical oscillator can be cooled to its quantum ground state, where it has the minimum possible energy allowed by the uncertainty principle. Quantum mechanics has applications in precision measurement, where mechanical oscillators can be used as ultra-sensitive detectors of force, acceleration, and gravitational waves. It also provides a platform for exploring fundamental questions about quantum mechanics, such as the boundary between quantum and classical behavior and the possibility of observing quantum superpositions of macroscopic objects. Experiments have demonstrated quantum control of mechanical motion, entanglement between light and mechanics, and the preparation of non-classical states of motion. Quantum optomechanics is a vibrant field that bridges quantum optics, condensed matter physics, and gravitational wave detection, offering new tools for probing the quantum world. Just as the no-cloning theorem states that you cannot create an exact copy of an unknown quantum state, the no-deleting theorem states that you cannot perfectly delete an unknown quantum state. If you have two copies of a quantum state and you want to delete one, leaving the other intact, quantum mechanics forbids this operation in general. The no-deleting theorem is a consequence of the linearity and unitarity of quantum evolution. It has implications for quantum information processing, as it limits the ways in which quantum information can be manipulated and erased. The theorem is related to the reversibility of quantum operations and the conservation of information in quantum mechanics. Together with the no-cloning theorem, it highlights the unique nature of quantum information, which cannot be freely copied or deleted like classical information. The no-deleting theorem is a fundamental constraint that shapes the landscape of quantum computing and quantum communication. Cellular automata are discrete models where a grid of cells evolves according to local rules, used to study complex systems and emergent behavior. Quantum cellular automata extend this concept to the quantum realm, where each cell is a quantum system and the evolution rules are quantum operations. Quantum cellular automata can exhibit behaviors that are impossible classically, such as superposition of configurations and entanglement between distant cells. They provide a framework for studying quantum computation, quantum simulation, and the foundations of quantum mechanics. Quantum cellular automata have been used to model quantum walks, quantum field theories, and even quantum gravity. They offer a discrete, algorithmic approach to quantum dynamics, complementing the continuous framework of the Schrödinger equation. Quantum cellular automata are also being explored as a model for universal quantum computation, where any quantum algorithm can be implemented by designing appropriate local rules. They represent a bridge between computer science and physics, showing how computation and physical law are deeply intertwined. In classical physics, if a particle is moving to the right, its probability of being found to the right increases over time. But in quantum mechanics, a phenomenon called quantum backflow can occur, where a particle with positive momentum can have a decreasing probability of being found to the right. This seems paradoxical, as the particle is moving forward yet its probability distribution shifts backward. Quantum backflow arises from the interference of different momentum components in the wave function. It is a purely quantum effect with no classical analog, and it has been predicted theoretically and observed experimentally. Quantum backflow is a subtle effect, limited in magnitude and duration, but it illustrates the counterintuitive nature of quantum probability and the role of interference. It challenges our classical intuition about motion and probability, showing that in the quantum world, the relationship between momentum and position is far more intricate than we might expect. Entanglement is the most famous form of quantum correlation, but is not the only one. Quantum discord refers to a broader class of quantum correlations that can exist even in separable states where there is no entanglement. Discord measures the difference between two ways of extracting information from a quantum system, measuring one part and inferring the other, versus measuring both parts jointly. In classical systems, these two approaches yield the same information, but in quantum systems, they can differ, and this difference is quantum discord. Discord is present in many quantum states that are not entangled, and it has been shown to be a resource for certain quantum information tasks, such as quantum state merging and remote state preparation. The discovery of quantum discord revealed that entanglement is not the only form of quantum correlation, and that the boundary between quantum and classical is more nuanced than previously thought. Discord has been measured experimentally and is being explored for applications in quantum computing and quantum communication. It reminds us that the quantum world is rich with subtle correlations that defy classical description, and that our understanding of quantum resources is still evolving. The Quantum Approximate Optimization Algorithm, or QAOA, is designed to tackle combinatorial optimization problems, which are ubiquitous in fields like logistics, finance, and machine learning. These problems involve finding the best solution from a vast set of possibilities, and they are often NP-hard, meaning no efficient classical algorithm is known. QAOA works by encoding the problem into a quantum Hamiltonian, a mathematical object that describes the energy of the system. The algorithm then applies a sequence of quantum operations that alternate between the problem Hamiltonian and a mixing Hamiltonian, which explores different solutions. The parameters of these operations are optimized classically to minimize the energy, which corresponds to finding the best solution. QAOA is particularly suited to near-term quantum computers because it uses relatively shallow circuits and can provide approximate solutions even with noisy qubits. Researchers are studying how QAOA performs on various problems and how it compares to classical algorithms. Early results suggest that QAOA can find good solutions efficiently, though whether it offers a true quantum advantage is still an open question. QAOA represents a practical approach to harnessing quantum computing for real-world optimization challenges. To fully characterize a quantum state, you need to perform quantum state tomography, a process that involves making many measurements on many identical copies of the state. Because a quantum state is described by a wave function or density matrix, which contains complex numbers and many parameters, you cannot determine it from a single measurement. Instead, you must measure different observables, each revealing partial information about the state, and then reconstruct the full state from the combined data. For a single qubit, this requires measuring in at least 3 different bases. For larger systems, the number of measurements grows exponentially with the number of qubits, making full tomography impractical for large quantum systems. Researchers have developed techniques like compressed sensing and machine learning to reduce the number of measurements needed and to perform tomography more efficiently. Quantum state tomography is essential for verifying that quantum devices are working correctly and for characterizing the states produced in quantum experiments. It is a fundamental tool in quantum information science, providing a bridge between the abstract mathematical description of quantum states and the concrete reality of experimental data. The quantum Zeno effect can be generalized to protect not just a single state but an entire subspace of states. By frequently measuring whether the system is within a particular subspace, you can confine the evolution to that subspace, preventing transitions to states outside it. This is called the quantum Zeno subspace, and it has applications in quantum error correction and quantum control. By designing measurements that projected onto a protected subspace, you can shield quantum information from certain types of errors, while still allowing useful operations within the subspace. The quantum Zeno subspace has been demonstrated experimentally and is being explored as a tool for building robust quantum gates and preserving quantum coherence. It is an example of how the measurement-induced dynamics of quantum systems can be harnessed for practical purposes, turning a potential obstacle into a resource for quantum technology. Atomic clocks, which use the quantum transitions of atoms to measure time, are the most accurate timekeeping devices ever built. They are so precise that they can detect the effects of general relativity, such as time dilation, over distances of just a few centimeters. According to Einstein's theory, time runs slower in stronger gravitational fields and for objects moving at high speeds. Quantum clocks have been used to measure these effects with unprecedented precision, confirming the predictions of relativity and opening new possibilities for geodesy, navigation, and tests of fundamental physics. Quantum clocks are also being explored for applications in the quantum internet, where synchronized time is essential for coordinating quantum operations across distant nodes. The development of portable, highly accurate quantum clocks could revolutionize global positioning systems and enable new forms of precision measurement. Quantum clocks are a beautiful example of how quantum mechanics and relativity intersect, and how the strange rules of the quantum world can be harnessed to probe the fabric of space-time itself. There are two main paradigms for quantum computing: gate-based and quantum annealing. Gate-based quantum computing, the more familiar approach, uses sequences of quantum gates to manipulate qubits and perform computations much like classical computers use logic gates. This approach is universal, meaning it can implement any quantum algorithm, but it requires precise control and error correction. Quantum annealing, by contrast, is a specialized approach designed for optimization problems. It uses quantum tunneling and thermal fluctuations to explore the energy landscape of a problem and find the lowest energy state which corresponds to the optimal solution. Quantum annealers, such as those built by D-Wave, are easier to build and scale than gate-based quantum computers, but they are not universal and are limited to certain types of problems. The debate over which approach is superior is ongoing, and it may be that both have their place, with gate-based computers handling general-purpose tasks and quantum annealers tackling specific optimization challenges. The two paradigms reflect different ways of harnessing quantum mechanics, and both are pushing the boundaries of what is computationally possible. The Jarzynski equality is a remarkable result in statistical mechanics that relates the work done on a system during a non-equilibrium process to the free energy difference between the initial and final equilibrium states. It holds even when the process is far from equilibrium, and it has been extended to the quantum realm. The quantum Jarzynski equality has been tested experimentally using trapped ions and other quantum systems, and it provides a way to measure free energy differences by performing many repetitions of a process and averaging the work. The equality has applications in understanding quantum thermodynamics, nanoscale engines, and the role of information in thermodynamic processes. It also connects to the foundations of quantum mechanics, as it involves the interplay between quantum measurement, work, and entropy. The quantum Jarzynski equality is a bridge between thermodynamics and quantum information, revealing deep connections between energy, information, and the arrow of time. Quantum radar is a proposed technology that uses quantum entanglement to detect objects with greater sensitivity and stealth resistance than classical radar. The basic idea is to generate pairs of entangled photons, send one photon toward the target, and keep the other as a reference. The reflected photon is then compared with the reference photon, and the entanglement provides a correlation that can be used to detect the target even in the presence of noise and jamming. Quantum radar could potentially detect stealth aircraft, which are designed to evade classical radar, and it could operate at lower power levels, making it harder to detect. The technology is still in the research phase, with experiments demonstrating proof of concept in laboratory settings. Challenges include maintaining entanglement over long distances and in noisy environments, and scaling the technology to practical sizes. Quantum radar is an example of how quantum mechanics can be applied to defense and sensing, offering capabilities that go beyond what is possible with classical technology. One of the major challenges in building a quantum internet is the loss of photons as they travel through optical fibers. After a certain distance, the signal becomes too weak to detect, limiting the range of quantum communication. Quantum repeaters are devices designed to overcome this limitation by dividing the communication channel into shorter segments and using entanglement swapping to create entanglement across the full distance. A quantum repeater consists of quantum memories, which store quantum states, and entanglement generation and swapping operations. By creating entanglement between adjacent segments and then swapping the entanglement, the repeater can extend the range of quantum communication without directly transmitting the quantum state over the full distance. Building practical quantum repeaters is a major engineering challenge, requiring high-fidelity quantum memories, efficient entanglement generation, and error correction. Researchers are exploring various physical implementations, including atomic ensembles, trapped ions, and solid-state systems. Quantum repeaters are essential for realizing a global quantum internet, enabling secure communication and distributed quantum computing over intercontinental distances. The Margolis-Levitin theorem sets a fundamental limit on the speed of quantum computation. It states that the minimum time required for a quantum state to evolve into an orthogonal state is inversely proportional to the energy of the system. This means that there is a trade-off between energy and speed. To compute faster, you need more energy. The theorem is a quantum version of the speed limit, and it applies to any quantum process from quantum gates to quantum algorithms. The Margolis-Levitin theorem has implications for the design of quantum computers, as it sets a bound on how quickly quantum operations can be performed. It also connects to thermodynamics, as the energy required for computation is related to heat dissipation and entropy production. The theorem is a reminder that even in the quantum world, where so much seems possible, there are fundamental limits imposed by the laws of physics. It shows that speed, energy, and time are deeply intertwined, and that the quest for faster computation must reckon with these fundamental constraints. One of the great unsolved problems in physics is the unification of quantum mechanics and general relativity into a theory of quantum gravity. General relativity describes gravity as the curvature of space-time, while quantum mechanics describes the behavior of particles and fields at the smallest scales. The two theories are incompatible in their current forms, and reconciling them is one of the deepest challenges in theoretical physics. Loop quantum gravity is one approach to this problem. It proposes that space-time itself is quantized, made up of discrete loops and nodes, rather than being continuous. In this framework, space has a granular structure at the Planck scale, the smallest scale at which the concepts of space and time are meaningful. Loop quantum gravity makes predictions about the behavior of black holes, the early universe, and the nature of singularities, and it offers a way to understand gravity without requiring extra dimensions or supersymmetry. The theory is still being developed, and it faces challenges in making testable predictions and connecting to observable phenomena. Loop quantum gravity is a bold attempt to extend the principles of quantum mechanics to the very fabric of space-time, and it represents one of the frontiers of fundamental physics. Entanglement is not just a feature of isolated quantum systems in laboratories. It also plays a crucial role in condensed matter physics, the study of materials and their properties. Many exotic states of matter, such as topological insulators, quantum spin liquids, and high-temperature superconductors, are characterized by long-range entanglement, where particles are entangled across macroscopic distances. This entanglement gives rise to emergent phenomena that cannot be understood by looking at individual particles alone. For example, in a quantum spin liquid, the spins of electrons are entangled in a complex pattern that prevents them from ordering into a regular magnetic structure, even at zero temperature. Understanding and characterizing entanglement in condensed matter systems is a major area of research, with implications for developing new materials and technologies. Entanglement is also being explored as a resource for quantum computing, as certain condensed matter systems can be used to encode and manipulate quantum information. The study of entanglement in condensed matter reveals that the quantum world is not confined to the microscopic realm, but extends to the materials and devices we use every day. The no-broadcasting theorem is a generalization of the no-cloning theorem. It states that it is impossible to create multiple copies of an unknown quantum state and distribute them to different recipients, a process called broadcasting. While the no-cloning theorem forbids perfect copying, the no-broadcasting theorem goes further, showing that even approximate broadcasting is impossible for arbitrary quantum states. This has implications for quantum communication and quantum cryptography, as it limits the ways in which quantum information can be shared. The no-broadcasting theorem is a consequence of the linearity of quantum mechanics and the monogamy of entanglement, which states that if two particles are maximally entangled with each other, they cannot be entangled with a third particle. The theorem highlights the unique nature of quantum information and the constraints that govern its manipulation. It is a fundamental result that shapes the landscape of quantum information theory and underscores the differences between quantum and classical information. Black holes, regions of space-time where gravity is so strong that nothing can escape, have long been a puzzle for physics. They seem to destroy information, violating a fundamental principle of quantum mechanics, that information is conserved. This is known as the black hole information paradox. Recent research suggests that quantum entanglement may hold the key to resolving this paradox. According to the holographic principle and the AD/CFT correspondence, the information that falls into a black hole is not lost, but is encoded in the entanglement structure of the quantum fields near the event horizon. The interior of the black hole and the radiation it emits are connected by a web of entanglement, and the information is gradually released as the black hole evaporates through Hawking radiation. This idea has led to the concept of the air equals sign EPR conjecture, which proposes that entangled particles are connected by tiny wormholes, linking quantum mechanics and general relativity in a profound way. The study of entanglement in black holes is at the frontier of theoretical physics, offering glimpses of a deeper theory that unifies quantum mechanics and gravity. It reveals that entanglement is not just a feature of quantum systems, but may be woven into the very fabric of space-time. Birds possess a remarkable ability to navigate across vast distances, using the Earth's magnetic field as a compass. Recent research suggests that this navigation may rely on quantum mechanics. The leading theory involves a protein called cryptochrome found in the retinas of birds. When light strikes cryptochrome, it creates a pair of electrons in an entangled state called a radical pair. The Earth's magnetic field influences the spin states of these electrons, affecting the chemical reactions that follow and producing a signal that the bird can sense. This quantum compass would allow birds to see the magnetic field as a pattern of light and dark overlaid on their visual field. The idea that quantum coherence can survive in the warm, noisy environment of a living cell was initially met with skepticism, but experiments have provided supporting evidence. Quantum biology is revealing that life may exploit quantum effects in ways we are only beginning to understand, from photosynthesis to enzyme catalysis to sensory perception. It suggests that the boundary between the quantum and classical worlds is not as sharp as we once thought, and that quantum mechanics may play a role in the very processes that sustain life. The measurement problem remains one of the deepest mysteries in quantum mechanics. Before measurement, a quantum system exists in a superposition of states, evolving smoothly according to the Schrödinger equation. But when a measurement is made, the superposition collapses into a single definite outcome, a process that is discontinuous and probabilistic. What causes this collapse? Is it the interaction with a macroscopic measuring device, the involvement of a conscious observer, or something else entirely? Different interpretations of quantum mechanics offer different answers, but none is universally accepted. The Copenhagen interpretation treats measurement as a fundamental process, but does not specify what constitutes a measurement. The many worlds interpretation denies that collapse occurs, proposing instead that all outcomes happen in parallel universes. The pilot wave theory introduces hidden variables that guide particles along definite trajectories. Decoherence explains how interaction with the environment causes the appearance of collapse, but it does not explain why a particular outcome is selected. The measurement problem is not just a philosophical puzzle. It has practical implications for quantum computing, quantum cryptography, and our understanding of reality itself. It is a reminder that despite its extraordinary success, quantum mechanics is not yet fully understood. Building a large-scale, fault-tolerant quantum computer requires protecting quantum information from errors. The surface code is one of the most promising approaches to quantum error correction. It encodes logical qubits into a two-dimensional lattice of physical qubits, with each logical qubit represented by the collective state of many physical qubits. Errors are detected by measuring stabilizers, operators that check for certain types of errors without revealing the quantum information itself. When an error is detected, it can be corrected by applying the appropriate quantum operation. The surface code has several advantages. It requires only nearest neighbor interactions, making it easier to implement in hardware. It has a high error threshold, meaning it can tolerate a relatively high rate of physical errors, and it can be scaled up by adding more qubits. Researchers are actively developing surface code implementations using superconducting qubits, trapped ions, and other platforms. The surface code is a key technology for realizing the vision of universal quantum computing, enabling quantum computers to perform long, complex calculations without being overwhelmed by errors. It represents a triumph of quantum information theory, showing how the strange rules of quantum mechanics can be harnessed to protect information in a fundamentally noisy world. The many worlds interpretation proposed by Hugh Everett in 1957 offers a radical solution to the measurement problem. It suggests that when a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. In one branch, the electron is spin up. In another, it is spin down. All outcomes occur, but in separate, non-communicating parallel universes. there is no collapse of the wave function. Instead, the wave function of the universe evolves smoothly and deterministically, with observers becoming entangled with the systems they measure. The many worlds interpretation eliminates the need for a special measurement process and treats observers as part of the quantum system. It is a deterministic theory where the evolution of the wave function is governed by the Schrödinger equation alone. However, it raises profound questions. If all outcomes occur, what determines which branch we experience? How do probabilities arise in a deterministic theory? And is the proliferation of universes scientifically acceptable, or is it an extravagant ontology? The many worlds interpretation has passionate advocates and critics, and it remains one of the most debated topics in the foundations of quantum mechanics. It challenges our notions of reality, identity, and the nature of existence itself. Shor's algorithm, developed by Peter Shor in 1994, is one of the most famous quantum algorithms. It can factor large numbers exponentially faster than the best-known classical algorithms, a capability that has profound implications for cryptography. Most modern encryption schemes, such as RSA, rely on the difficulty of factoring large numbers. A classical computer would take thousands of years to factor a number with hundreds of digits, but a sufficiently large quantum computer running Shor's algorithm could do it in hours. This has sparked a race to develop quantum-resistant encryption methods and to build quantum computers capable of running Shor's algorithm. Shor's algorithm works by transforming the factoring problem into a problem of finding the period of a function, which can be solved efficiently using the quantum Fourier transform. The algorithm exploits superposition and interference to explore many possibilities simultaneously and extract the answer. Shor's algorithm is a landmark in quantum computing, demonstrating that quantum computers can solve certain problems that are intractable for classical computers. It has driven much of the investment and research in quantum computing and has brought the field from theoretical speculation to practical reality. Quantum technology is poised to transform many aspects of our lives, from communication and computation to sensing and medicine. Quantum computers promise to solve problems that are beyond the reach of classical computers, such as simulating complex molecules for drug discovery, optimizing logistics networks, and breaking current encryption schemes. Quantum communication offers unbreakable security through quantum key distribution and the potential for a global quantum internet. Quantum sensors provide unprecedented precision for measuring magnetic fields, gravitational waves, and time, with applications in navigation, geophysics, and fundamental physics. Quantum materials, engineered at the atomic level, could lead to new superconductors, batteries, and electronic devices. The development of quantum technology is a global effort, with governments, universities, and companies investing billions of dollars. Challenges remain, including scaling up quantum systems, reducing errors, and integrating quantum devices with existing infrastructure. But the progress over the past few decades has been remarkable, and the pace of innovation is accelerating. Quantum technology is not a distant dream, but an emerging reality, and it will shape the future in ways we are only beginning to imagine. As we reach the end of our journey through 100 facts about quantum physics, we arrive at a profound realization. The quantum world is not separate from the world we experience, but is its foundation. Every atom in your body, every photon of light that reaches your eyes, every chemical reaction that sustains life is governed by the strange, beautiful laws of quantum mechanics. The solidity of matter arises from the Pauli exclusion principle. The colors of the world emerge from the quantized energy levels of atoms. The warmth of the sun is powered by quantum tunneling in nuclear fusion. The devices you use every day, from smartphones to medical scanners, rely on quantum effects, and the very fabric of space-time may be woven from quantum entanglement. Quantum mechanics is not just the theory of the small, it is a theory of everything, a framework that describes the universe at its most fundamental level. It challenges our intuitions, defies our expectations, and reveals a reality far stranger and more wondrous than we could have imagined. As you drift into sleep, let these ideas wash over you like gentle waves. Each one a reminder that the universe is not a collection of separate objects, but a unified whole, shimmering with quantum possibilities, forever entangled in the dance of existence. Rest now and dream of the quantum realm, where the impossible becomes merely improbable, and the boundaries of reality dissolve into infinite potential. And so we conclude our exploration of 100 quantum facts, a journey through the invisible architecture of reality. From Planck's first quantum to the many worlds interpretation, from the double-slit experiment to quantum computers, we have traversed the landscape of the subatomic. Together, where particles are waves, where observation shapes reality, and where the universe is woven together by invisible threads of entanglement. May these ideas carry you gently into sleep, each fact a stepping stone into deeper relaxation, deeper wonder, and deeper dreams. The quantum world is always here, beneath the surface of the visible, shimmering with possibility, waiting to be explored. Good night, and may your dreams be as strange and beautiful as the quantum realm itself.